So what I just talked is how to use this um, software, and I gave a demonstrate one circuit. You can demonstrate, you can using that one to play with other kind of logic circuit. That the very good thing is the very easy to use, and also give you the corresponding Boolean algebra and also the truth table to do the analysis. Of course, the assumption is all those things is there's no memory, implemented that. Basically, there's no um potential states, or say the sequential element, the logic element inside. Okay, so again, in order we said if the based on that the component has a memory or not. If it does not have memory, we call it combinational component, right? If it has memory, we call it sequential memory. And if it's a combinational memory, basically does not have memory, we can using two types representation to describe the behavior. One is called truth table. Another one is called, I think here mentioned, another called Boolean algebra. Okay, so first I just want to describe a little bit why we want to using the digital system. The reason is because you can see all the input output data, also the state data, but used is only zero and ones, right? In other words, all the circuit inside is a digital electronic circuit. In other words, they only implemented by low voltage and high voltage. Therefore, when we talk about this computer architecture, all that is the digital systems, right? From the hardware perspective. And all those digital system is a discrete digital system, and also only has or involve the binary numbers. Okay, and here, right? For example, your analog system is this way. The digital system basically will be make it a discrete time step, has a discrete time step, also counts that with only zero and ones. Okay, again, based on whether, as I just mentioned, based on this component has a state or not, we will classify that into the combinational component or sequential component. Okay, if the combinational component base does not have memory, right? So that means the output only determined by the current inputs. But if it is a sequential element, basically it has memory, so the output is not only determined by the current input, also determined by the state or the memory in the component. What is the memory in the component? Means the previous inputs, or we say it's the state of the element. Okay, so in other words, the output of the sequential element determined by both of the current inputs and the states. Again, if we in this logic the tutorial of the digital system, we focus on describe the combinational and digital logic, or the combinational component which does not have memory, which means the output only determined by the current input, and you have to describe the behavior of those components. I can using the truth table and the Boolean algebra. So what means truth table? I believe many of you are very familiar with that. It's kind of straightforward. Basically, in each column, I will list all the potential input combination. And then, so, say one more time. And all the this way, all the column in the truth table, I will implement or indicate all the potential combination of the input. Okay, and then I will in the other those column, this column, all these columns will be give the corresponding output based on the combination of the input. Let me say one more time. The truth table include the two part, output columns, output columns and input columns. And the input columns indicate all the possible combination of the inputs, and the output columns will give the corresponding output associated with the specified combination of the input. And if you potentially has an n different input, you potentially will has 2 to n different combinations of the input. Therefore, you will, for each output, you will have 2 to n different potential values. Not different value, different situations, say this way. So in other words, if you have, if you're, you have n columns representing the input columns, the row of your truth table will have 2 to n rows. So one more time, if you have n inputs columns, you will have 2 to n rows because you have 2 to n different situation of the individual output. Okay, so for example, this one, if I want you to pause here to try to think, okay, so based on the given input, what do you think the logic of this output D? And what do you think the logic of the output F? And then what do you think the logic of the output E? I want you to pause here to try to figure out yourself. Okay, and then we continue. If you look at here, the D is all ones except the first situation when A, B, C both all zeros. So in other words, D indicate as long one of the inputs is 1, then the output D will be 1, right? Similarly, if you look at the F, okay, so basically only all others are 0. Only 1 is 1, which is when A, B, C are all 1. So that means the output F means F will be 1 only when all A, B, C are 1s. In other words, F will be true if all the 3 inputs are true. And then E is a little bit tricky, right? It only has a 3 case are 1, but when you look at the 3 case, each of the case there are 2 inputs are 1. In other words, E will be 1 if 2 of the inputs are 1. And then this 2 is exactly 2. Cannot be 3, cannot be 1, right? Say one more time, like I mentioned here, the output E will be true if exactly 2 inputs are true. Okay? So again, each row of this truth table with column and entry will indicate the one specific combination of the input and the corresponding output. And as I mentioned, you have the, like in this case, you have 3 inputs. Therefore, you can see you will have 3 entries in this truth table because there will be, sorry, say one more time. You have 3 inputs in this truth table, so you will have 2 to 3. Basically, it's 8 entries in this truth table because you will have 3 input. You will have 2 to 3, which is 8 different situations for the individual output. And truth table is good because it helps you to visualize all the situation. This method is really good when you not quite understanding the circuit yet. You try to do some experimental validation. During that time, truth table help you to visualize all the performance of the system. The disadvantage is also obvious. Basic disadvantage is the dimension of this truth table will be exponentially increased when your complexity of the circuit is increased, because you can see you will have n input, you will totally will have 2 to n entries. It will be exponentially increased. So basically it means this method is good, it's straightforward, but it's not that practical for the big systems. So what is the practical one? Practical one for the complex combinational system is Boolean algebra. The difference from truth table is not that visualizable, but the good thing is using logic equation can express the behavior of the circuit in a more compact way. So for example, I can implement using A dot B to implement the AND operation between the component A and B. Or say, I will implement the AND operation by using the notation A dot B. And this also, each Boolean algebra has their corresponding truth table. For example, for this AND operation, the truth table is the following, right? Basically, the output will be 1 only when both A and B are 1. Similarly, I'm using A plus B to represent the operator OR. So the corresponding true symbol is following. Basically, only when both A and B are 0, the output will be 0. Similarly, I will implement an A or using the notation A bar to represent NOT operation. Corresponding true symbol is following. And basically, if the input is 0, output will be 1. If the input is 1, output is 0. Basically, flip the bits. So there's a different many different laws for the Boolean algebra. So many of them is, I believe, you're very familiar with. So I just highlight two. I think it's kind of not commonly recognized, but it's really kind of straightforward. Okay, so basic one is called 0 and 1 laws. Basically means if you try to implement or, okay, or operation. So that means as long as one of the input is 1, the output will be 1. I don't care the other input is what. Say one more time, if you implement OR operation, as long as one of the input is 1, the output will be 1. Similarly, if you implement the AND operation, as long as one of the input is 0, the output will be 0. So for the inverse laws means if you have two signals, one is the complement one of the another one. Basically means you have two inputs. One input can be achieved by implement the NOT through the another input. Then if I implement OR between these two inputs, the output always be 1. Similarly, if I implement AND operation between these two signals, the output always 0. Okay? So now let's go back to the original example to see whether we can use Boolean algebra to represent the corresponding D, E, F inputs. Okay, so this is the corresponding the truth table for that example. So because we just mentioned, right, D will be 1 as long as one of them are 1, will be 0 only when all of the inputs are 0. In other words, I can use OR this operation to represent, right? Basically means D is equal to A plus B plus C. Please pause here to think whether you agree. Similarly, F means F is 1 only when all of them are 1, will be 0 as long as one of them is 0. That exactly meets the definition of AND operator. Basically, F is equal to A dot B dot C. Basically means F can be achieved by implementing AND operation amongst A, B, and C. So the E is not straightforward, right? So basically the E is when E is 1 when there are exactly two inputs are 1. So how you implement that? There's one way kind of straightforward. I just list all of them. Let me mention here. I just list all of them, okay? So basically means you can see when E is the first one is what? Means B and C are 1 and A is 0. So basically I will do B, C itself, and then A not. So and then I will implement these three cases by using AND operation. Another one, E is 1 when A and C are 1, B is 0. So means A and C are the self, and B I need to do B not. And then I will implement the AND operation between them, amongst them. Similarly, E is 1 when A, B are 1, C and 0. Means I implement A and B self and C not, and then using AND operation to implement amongst them. Okay, so this is kind of way is at least all the cases. Another way is a logically operate. Means what? Means how about I can implement this way. Means at least two of the inputs are 1. And then I will exclude the situation all of them are 1. So one more time, to describe behavior of E, I can describe it as following. At least two of the inputs are 1, and then I exclude the situation when all of them are 1. So here, right? At least two of them are 1, but it cannot be all of them are 1. So in that case, at least two of them are 1 means what? I will list all the cases of two of them are 1, can be A, B are 1, AC11, BC11, and then I will list out this situation, but exclude the situation A, B, C, all ones. Okay, it means this part is at least two of them are one. This part will be all of them are one is not allowed. And then these two situations has to be satisfied at the same time. Therefore, I'm using AND operation to connect them. Okay. So again, there's a I want to mention there's different level to describe the digital logic component. And basically, the basic component is a gate. Okay, but and gate actually also built based on transistors. Okay, but the thing is that, as I mentioned, the subtraction is a very critical technique in learning engineer, and here subtraction means I only focus on at a certain level. Help me to understand this level is a gate level. Basically, we will not focus on transistors level. We only talk and stop at the gate level. Okay, so here just list some fundamental gate, and then there notation like AND gate, OR gate, and NOT gate, and their corresponding truth table. Those gates you already see when we just implement this logic sim, right? And then here also mention the precedence, right? So NOT has a higher priority compared with and AND has a higher priority compared with OR. For example, if we want to implement A and B naught plus A naught B, so equivalent to implement, or say this actually try to implement is we implement the not first, and then implement and second, and then implement or at the end. Okay, so besides that, we also have some other gates, for example, not and, not or, and exclusive or. You see, not and means what means not and? Not and means not and, right? Means A B, and then you need to do not. Just right, and this is equal to what? Is equal to A naught and plus B naught, right? Just demonstrate one. Right, so basically not and is not and is equivalent to A naught, B naught, and implement or. That is how you can get this one. Similarly, not or means not or is equal to A naught, B naught, and implement and. Similarly, exclusive or is represented as the following. Okay, there has a corresponding gate representation and the truth table. Just mention exclusive or means only when A and B are different, then the output will be 1, otherwise will be 0. Like here, A, B are both 0, output will be 0, A, B are both 1, output are 0, otherwise output are 1s. Okay, and here just introduce another terms. One is called a complete set, another called a minimum complete set. What means complete set means if I have a set, and then using those elements or those gates in the set, I can implement all the logic function. Then that set will be complete set. What means minimum complete set? Means if that set are complete first, and then if I remove any of that element, I cannot or maintain that completeness of the set. In other words, there's no redundancy in the complement set. Okay, so in that way, if you look at those examples, the first one definitely is a complete set, but that is not a minimum complete set. Means if I remove one of the element, I still can use the left element to implement all the logic functions. And basically like these two are the and not or not are the minimum complete set, because as using them I can implement all the logic function, but if I remove one of them, they will not implement all the logic function. Basically, these two are complete set with no redundancy. Another term called universal set. What I call universal set means first this set is both of these two sets are the complement set, and also there's also minimum complement set, right? Because if you remove one gate, there's nothing left, and also because of that, because only one gate in this complement set, that's why we call universal set. Okay, so basically it has a complement set, minimum complement set, and universal set. So here, just to give a simple proof why we call the universal set, because I really let me prove why we say it's a universal set, means I really can using this one gate to implement all the other functionality. One thing we all agree and or not together will be complement set, although there's a redundancy. So that means I can use this gate or this gate to implement the all of these three, then that means I can using this gate to implement all the other functionalities. So here I want to left here I give one proof. I want to left you to give proof. In next class we will talk about that specifically. Okay, that's it.